Welcome again, and this time we're going to discuss the GC, and I'm going to go ahead and let you look at this little PowerPoint with me, and we'll talk about how this device works. Gas chromatography, there's just some facts about it. 1955 is when it first came around. It's really just today, it's a very complex instrument, mostly computer controlled. You can manually or mechanically inject the samples. We will be manually injecting with a very, very, very tiny syringe. We'll be using microliter amounts, millionths of liters. It's amazing you can think a needle can drop that little of a material. The results are calculated. They aren't going to be necessarily printed out. I'll show you a way that you can just make sure you bring your phone with you so you can take pictures of the screens is the best thing for what we have. So what you have in gas chromatography, and we're going to be doing acetates. It won't necessarily all be acetates. We're going to be doing a bunch of esters, on the one we're going to do. So what you have is you have a column, and the column, you'll see it, essentially it's packed with what we call the liquid phase, and you install that in the machine. Ours is permanently mounted in the machine that we're going to be using, which is a very small machine. Samples then injected with a microliter syringe into the injection port where it gets vaporized and mixed into the carrier gas. It's usually helium, nitrogen, or argon. We have a very inexpensive machine. Our carrier gas is just air, so we are very limited in what we can analyze. Then the sample vapor gets between the moving gas phase, which is the carrier gas, and the stationary liquid phase, which is inside of the actual column itself. The time the different compounds are in the device in the vapor phase is a function of their vapor pressure. The more volatile they are, they arrive at the end of the column first and pass out into the detector. So essentially, you can see as they move out, sample in, sample out, the gas moves them through. The stationary phase latches on or grabs onto them. So different polarities of the molecules. You can decide what you want to be on the stationary phase. It's a heavy liquid coated onto it's coated onto metal, essentially. It's a very, very tiny metal column that has this heavy liquid impregnated on the sides of it. So the polarity of the molecules coming in, they're attracted to the stationary phase, and the mobile phase keeps pushing them along. And so the ones that bind to the stationary phase more are going to stay behind longer, and the ones that are more volatile and in essence are not related to each other polarity-wise are going to get out of the machine faster. So if we were to look down through that column, if you look at it, you can see the A there. The A is the stationary phase, and the light A's, blue I guess you would say. And then the black A's are the mobile phase moving through. So there's an actual mathematical relationship between them, between what's going down through there. So that our material is moving down through that tube and is being attracted to that material that's in the middle there. So you can see what happens is as they come out of the detector will just, when you start it, you'll start a timer essentially on the computer, and the computer will analyze when it senses that chemical has come out of the machine. So the faster they come out, the less likely they were bound to that stationary phase that was inside of the machine. So you can see if you had this is just a simple two compound mixture. As it moves through the machine, you can see that the red one was attracted more, and the gray one was attracted less, and it was more volatile and came out of the machine faster. So here's a 3-component mixture, and you can see what it would look like on the GC. And what we have is some relationships here. We really don't care about the time because the time that they come out, all we want is that the machine separates our two materials. You can see that there's a good separation between the first two and the third one, but there's not really that great of a separation between the first and the second materials, if you'll notice, because the two hills, for lack of a better term, we call them peaks in this. The two peaks, you'll notice it does not come back to the baseline, so it's going to be harder for the computer to analyze that when it goes into it. And there's some tricks you can teach the computer to do that. Our rudimentary system that we're going to be using doesn't have all those bells and whistles, but an expert on a machine could do that. But what we'd want to do would be change our flow rate or something to be able to leave it in the machine a little longer. And if you don't push the material through the machine quite as fast, then what will happen will be that the materials will, if they linger a little longer on the stationary phase, then we can obtain a better separation of the materials. So that's just a schematic of what's going on inside. This is kind of a side view of what 1.1 looks like. Very crude little picture. That's the machine we used to have with an auto sampler unit on it. And then there's different methods that are used. There's an injection port, direct injection, or you have an auto sampler. We will be doing direct injection. That's the auto sampler, or that's the port, what it looks like. Then inside of it, that's the column that looks like that little thin wire there. And then the columns can be packed or they can be capillary. And the capillary has very little material in it. It's just thousands and thousands of trips around that the machine makes. The wire is about as thick as a human hair. Where in the top one, it's more of a packed column and there's fewer loops. As you can imagine, you get better separation in the capillary than the packed. So nonpolar versus polar molecules, just to refresh your memory on that. And there's two kinds of detectors. The detectors, essentially, what they do is one is exposed to the sample gas and the other one is exposed to a reference flow of the carrier gas. So in other words, inside of the machine, the air goes through and is split down two columns. And in essence, what the machine is doing is comparing the time it takes to get through the sample gas column as compared to the reference carrier gas flow, and that's how it determines the times. So the kind of there's different kinds of detectors that are in the machines. Ours is a very, very simple one. We don't use any of the flame detectors. They're destructive and tear up your samples. Non-destructive, there's thermal conductivity, electron capture, and photoionization. Ours uses thermal conductivity. So it's just a temperature difference. And in essence, if you think about this, it really does make sense that there's a little heated wire in there. And what happens is, as the air is flowing over the wire, it gets a certain resistance that is recorded by the machine. And it turns out that if anything else is mixed with the air, you get a different resistance. And that's essentially what the detector is detecting, is when does it sense it doesn't compare the resistance of the straight air and it's seeing something different. So that's if you care about the schematics of it, that's how those work. And most of these, they really don't mean much to them. That just talks about some of the other ways that you can have detectors. Here's a very complicated chromatogram of what we're going to be doing. And that's not what we will do. Ours is going to be very simply, what we're going to have to do is, though, for the retention time, is you're going to have to do some mathematics on it. And what I'm going to do is go ahead and, even while we are distilling in that, I'm going to talk to you. I'm just going to show you on the board how to calculate the retention times rather than try to show it to you here. But so what we will do is we will use, for the most part, the triangulation. We won't have to use the triangulation method because our machine will actually give us our percents as we do them. So you'll get to see that. You won't have to do the fancy math, but If you do have to do it, which you will have to do on a final, essentially the triangulation method is real simple. When you measure the height of the peak, what you do is to get the area under the peak, this is a real simple way, you measure the height of the peak and then take half of that and measure the width at the half height. So our area then, for example, you're going to have two different separate peaks that you'll collect at different times. So you'll do that method of the half height, the width at the half height times the height, and you'll get your areas and you'll add them up, and then you can see there the simple math that you have to do. And I'll show you an example of that on the board as we do that. So we're going to make we made the isoamyl acetate, the banana oil. You've already done all that part there. So this just gives you all the parts of the experiment that you've already done. And let me skip through all that and get us up to where, and that's it. So we'll go with that and let you guys have all that data there, and we'll put that all together, and on Thursday night we'll have, the problem is we only have 2 of the machines, maybe 3. It takes about 5 to 8 minutes to run it, so first people done with their distillations are going to be the first guys into the GCs. So we'll run it from there. There's kind of a quick run through of it, but we'll have more to come.